All right, we have a problem here. The burner on an electric stove has a power output of 2 kilowatts. A 720 gram stainless steel tea kettle is filled with 20 degrees Celsius water and placed on the already hot burner. If it takes 3.8 minutes for the water to reach a boil, what volume of water in cubic centimeters was in the kettle? Stainless steel is mostly iron, so you can assume its specific heat is that of iron. So I looked that up on the test notes. C of iron on our table in the test notes is 449 joules per kilogram Kelvin. We have water in this kettle, so I looked that up as well. That's 4190 joules per kilogram Kelvin. All right, so two things happening here. Power, you might have to revisit chapter, when did we talk about that? Chapter 9, I think it was. I can't remember for sure off the top of my head. Power, though, is energy per time. So a watt is a joule per second. So we know this power, and we're given the time as well. And so knowing the power output and the time, we can figure out how much energy is put into this system, which consists of the kettle and the water. Okay, I'll go ahead and just find that at the moment. So 2,000, because we have 2 kilowatts, we have to put in the 10 to the positive 3 to have the watts. 3.8 minutes, we will want that in seconds because a watt is a joule per second. So a minute has 60 seconds. So 2,000, 3.8 times 60. I'm going to put it down here. 4.56 times 10 to the 1, 2, 3, 4, 5 joules of energy are being put into the system. Now it's heat energy, so we can say the total Q being put into this system is this 4.56 times 10 to the 5th joules. We know we have this water in this tea kettle. All of that energy here is being shared and put into the kettle and the water. So we can essentially say the Q of the system, this is our Q of our system, this energy is going into both the kettle and the water. So we're trying to find out how much water we have, and specifically the volume. As we look at this, we need to determine which equation to use, or equations. It's possible to use both equations in a problem. So we know we start with an initial temperature of 20 degrees Celsius. That's the water. We can assume the kettle is also 20 degrees Celsius. It doesn't specifically state that, but 20 degrees Celsius is about room temperature. Because the iron has such a small specific heat capacity compared to water, that iron's temperature is going to change very quickly. So we'll go ahead and just assume the initial temperature of both iron and the water are 20 degrees Celsius. And we're told that we get the water to reach a boil, which means we get to the boiling temperature of water which this is on the table as well. That's 100 degrees Celsius. So in this particular problem, we're just looking at getting the water to a boil. We're not going to calculate anything about boiling, how much energy is needed to boil water off. And so we actually only need MC delta T in this case. So we'll need the mass of the iron, C of the iron, delta T of the iron to account for the tea kettle, plus mass of the water, C of the water, delta T of the water. We know how much energy we have going into the system. We found that from the power and the time. We know the mass of the iron is 720 grams, which we will want in kilograms. We have our C values. Our delta T, our change in temperature, final minus initial, is going to be the same. They both are going to end up at 100 degrees Celsius. They both start at 20 degrees Celsius. And so delta T in this case for iron is the same as delta T for water, which is going to be 100 minus 20, so 80 degrees Celsius, or 80 Kelvin. That change, delta T, is the same whether we're talking Celsius or Kelvin. So we know Q of the system, we know this, we know the mass, we know C delta T. Our only unknown is the mass of this water. And so we will be able to figure out the mass of the water. Oops, let's subtract that term. So subtracting mass of the iron, C of the iron, delta T of the iron. It's going to leave me with MC delta T for water. I'm going to go ahead and divide by the C delta T of water. Now, we are looking for volume, but let's go ahead and get the mass first. So we know the energy going into the system. We know the mass of the iron. We know the C of the iron. We know the change in temperature of the iron. Dividing by C of the water and the delta T of the water, this is going to give us the mass of our water. So 1.283, this is in kilograms. So we have joules here, we have joules here, we have joules per kilogram Kelvin, and then Kelvin. So the Kelvins cancel, the joules all cancel, so we end up with 1 over kilograms in the denominator, which gives us kilograms overall. Here we want to know the volume, not just the mass. Mass and volume are always related by density. So we've been using density as we talk about fluids. That's still true. So the volume will be the mass divided by the density. Off the table, the density of water is 1,000 kilograms per cubic meter. So 1.283 kilograms over 1,000 kilograms per cubic meter, 0.00. 2, 3, so 1,283. This would be meters cubed. To get it to centimeters cubed, we know there's 100 centimeters in a meter. We have to cube the entire conversion. So we're going to be multiplying that by 100 cubed. That makes it a big number. So we have approximately 1,300 centimeters cubed. And because the problem asked specifically for centimeters cubed is why I'm putting it into centimeters cubed. It would probably, in terms of what we're familiar with, make sense to write it in liters. That would be 1.3 liters of water. All right, so looking at the energy just to bring these two materials up to that final temperature and relating it to that power.